grid, and everything to the left of the grid, Pacific Ocean, and everything to the right of the grid and everything below the grid is going to be the Atlantic Ocean. So for any particular cell, we want to know, can this cell reach the Pacific Ocean and can it reach the Atlantic Ocean? If it can, then we are going to include this position in the result. If it cannot reach the Atlantic and Pacific Ocean, then we don't include it in the result. So how do we know if this cell can reach the Pacific and Atlantic Ocean? Because clearly there's a path, straight to it. Well, there's one condition. We want to know if water from this cell can flow to the Pacific and to the Atlantic, and water can only flow from the perspective of a cell to an adjacent cell that has a value that is lower than the original cell or equal to the cell. And it can only flow in 4 directions: straight above, to the left, to the right, and below. That's pretty straightforward. Usually you can't go diagonally in these types of graph problems. And so in this case, for this 5, we see that the above neighbor 3 is less than 5, this is less than 5, this is less than 5, and this is less than 5. So clearly 5 can go to all of its neighbors. Now let's take a look at the 3. Okay, 3 has a neighbor 1. 1 is less than 3, so it can definitely flow in that direction. And now see, this 1 is bordering the Atlantic Ocean. So clearly that means 5 is able to reach the Atlantic Ocean. Now let's look left. It can reach 4, and 4 can definitely reach 2 because 2 is less than or equal to 4. So from this perspective, we can also now reach the Pacific Ocean. So water from this position can flow to the Pacific and it can flow to the Atlantic. So this position is going to be included in our result. So a brute force and naive way to solve this problem is to simply go to every single position, do some kind of graph traversal, DFS or BFS would probably work, and doing that search, check from a cell, can we reach the top and left border, and can we reach the right and bottom border? And if we can, then we're going to add this cell to the solution set. If we can't, then we don't add it, right? So if we're doing a DFS or BFS on every single position, starting at every single position in the grid, we're going to get a time complexity of basically the size of the grid. Let's say that's n times m, which is, the dimensions of the grid. And if we do that from every single starting point, we're going to get n by m squared as the big O time complexity. And you might think, well, since we're doing this recursively, we're probably doing a lot of repeated work, right? So for example, if I'm starting at 3, right, doing a DFS from here, I'm going to go to its neighbors and then do DFS from here, 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 and here. And maybe, by doing that, I can cut out the repeated work, right? And so we won't have to, restart a DFS for every single position in the entire grid. And you might think that that will work, but I'm pretty sure it doesn't. I'm not going to go through the details of why, and somebody in the comments can correct me if I'm wrong. Maybe there is a clever way to get that to work, but I tried to do it myself and I was not able to, so I don't know if it's actually possible to do it that way. There's a different clever way to solve this problem. How about, rather than us going through every single cell and checking if this cell can reach Pacific and reach Atlantic, how about we go start from the Pacific Ocean, right? And let's find every cell that borders the Pacific Ocean. Clearly, everything in the first row borders the Pacific Ocean, right? That means everything in this cell can reach the Pacific Ocean, and everything in the left column can also reach the Pacific Ocean. And starting from each of these nodes, what we're going to do is now find what are all the other nodes that can also reach the Pacific Ocean, right? So at the end, we would have, some kind of set, maybe, it looks something like this, right? Or whatever. And then we know, okay, these are all the ones in purple can reach the Pacific Ocean. And similarly, we would also do that with the Atlantic Ocean. We know everything here on the right side can reach the Atlantic Ocean. Everything at the bottom can reach the Atlantic Ocean. And similarly, we do some kind of graph traversal starting from each of these positions, right? And see, okay, what nodes can reach the Pacific Ocean as well. And at the end, we would want to go through every single position in the grid, and we'd want to find positions like this one that can reach the Atlantic and Pacific Ocean, that we marked as being able to reach the Atlantic and Pacific. And then from these ones that can reach both, we would add them to our result and then return the result. So that's kind of the general algorithm of how we're going to do things. The reason this is more efficient, this is going to be big O n times m. We're not going to be revisiting nodes several times. We're not going to be rerunning a graph traversal. What we're going to be doing is starting at each of these nodes, right? Doing a depth first search, right? So for example, let's say we started at this one, right? We'd do a depth first search and then see all the other nodes that can reach the Pacific Ocean, right? Let's say we marked these and these, right? And then maybe we'd do the same thing starting at this one, right? And we'd, go over here maybe, and then go over here, and then we'd come back here. If we ever got to a cell that we revisited, we would not want to continue our depth first search from a repeated cell, right? So we just wouldn't do that. So that's the main idea of this algorithm, but there's one last point I want to make before I start going through the code. And that is, remember how if we're starting at a cell like this one, water can flow from this cell to a cell that has a smaller value, right? Like a small cell like 3, for example, and then it can flow down to a smaller cell like 1, and then it can reach the ocean, right? So if we are starting from a cell and reaching the ocean, we are allowed to go at equal heights, so 1 can reach 1, or we can go in decreasing heights like these ones. But if we're going in the opposite direction, if we're starting at the Atlantic Ocean and going to a cell like 1, going to a cell like 3, and going to a cell like 5, then we're going to have to do the opposite. We can go to cells of equal heights or cells of increasing heights, right? You kind of see why that's the case, because what we're saying is water is allowed to flow from 5 to 3 to 1, so therefore water from the ocean is allowed to go from 1 to 3 to 5, because that does mean that 5 can reach the ocean. So with that being said, the first thing I'm going to do is go through the first row, which is going to be Pacific Ocean values, and then from there I'm going to run depth first search to see all the other nodes that can reach the Pacific Ocean. And I'm going to do the same thing at the bottom row, seeing which nodes can reach the Atlantic Ocean. And I'm going to be maintaining those in a set, let's call it a visit set. It's going to be a hash set so that we don't end up adding duplicates to it. So now getting into the code, so the first thing I like to do with these problems is just get the dimensions of the grid. So we're guaranteed that this grid is not going to be empty, so we don't have to, worry about that. So let's get the length of heights, which is going to give us the number of rows, and then get the number of columns as well. And so I'm going to be having 2 hash sets, Pacific and Atlantic, maintaining all the positions that can reach the Pacific and Atlantic Oceans respectively. And then what I'm going to do is I'm going to go through every single position in the first row. So I'm going to go through every single column in the first row, right? And what's going to be every single position in the first row? From here, it's going to be zero, right? In the first row is 0, and column is going to be the column position. And so what I want to do on this position is run a DFS, right? So I'm going to run a DFS on this position, right? And so I'm going to pass in a visit set to this DFS function. Since this is the first row means it's the Pacific Ocean, right? It's not the Atlantic, it's the Pacific. So that's what I'm going to pass in as the visit set, the Pacific Ocean. So I want to visit this position and I want to see all the other positions it can reach. Now, we know that water from the ocean to other cells can only go at equal values or greater values, right? Remember, we reversed the thinking. Since we're going from the ocean to the cells, we're going to have to do the opposite. So we can go to greater cells. So I want to always pass in a previous height variable to this. So if we're going to visit a cell, I want to make sure that we're allowed to visit that cell. So I'm going to pass in a previous height. So since there is no previous height for this position, I can just give it a default value and I'll just give it the same height as this position because that's going to be allowed. Remember, we're always allowed to visit heights of the exact same height as the previous position. And so while we're at this, right, we're going through every position in the first row. Why not go through every single position in the last row, which tells us the Atlantic Ocean, right? So what's the last row? It's going to be the number of rows minus 1, and going through every column in that rows. And so instead of passing in Pacific, let's pass in Atlantic, because the bottom row refers to the Atlantic Ocean. And similarly, we'll pass in the height of this position as the previous height. So we're calling this DFS function, so let's might as well define it up above here now. The first two parameters are going to be the row and column, and the next is going to be the visit set. Now, since we're reusing this function for both Atlantic and Pacific, we'll just give it a generic name like visit. We could be passing in either of these two sets. And the last parameter is the previous height. So if this position has already been visited, meaning if row column is in visit, then we're going to return. We're not going to continue this function. Or if it's out of bounds, we're also not going to return, right? Because remember, we're already going from the ocean, from let's say the Pacific Ocean, and trying to visit all the cells that we can, because that's going to tell us all the cells that can reach the Pacific Ocean. So we're not even trying to reach the ocean right now. We're going from the ocean to all the